So now let's talk about procedures and how we actually measure the airflow and the fan wall draw with the equipment that we just described. Before we start talking about the procedure, let's talk about the exceptions to this particular test. So the airflow rate, fan wall draw, and determination of fan efficacy is not required when any of the following conditions apply. Either the system is not ducted, or the system does not have air conditioning. And keep in mind that non-zone systems may install return ducts and grills in accordance with Table 4-10 and 4-11 in the Residential Compliance Manual, or 150.0C and 150.0D in the standards, in lieu of conducting the adequate airflow and fan wall draw test, as previously discussed in the Title 24 overview section. There are two procedures that we will discuss in this section: the system airflow rate, which you may also hear referred to as the adequate airflow, return adequate airflow, and the fan wall draw. The system airflow rate, for systems utilizing an intentional ducted ventilation airflow from outside the conditioned space into the return system, the outside airflow may be included in the system airflow if that flow occurs in all operating modes of the HVAC system.
For multi-zone systems that utilize a single speed compressor, the airflow must be measured for each and every operating mode of the system. This must be accomplished without bypasses from the supply ductwork to the return ductwork. Now, what do they mean by every operating mode? So for a multi-zone system, you will have two or more zones within the home. For example, a living zone and a sleeping zone, could be an upstairs and a downstairs for a two-story home, but it's going to have multiple zones. So what you must do is you must test it with each individual zone operating. So you would test the downstairs only, then you would test the upstairs only, and then you would do a third test with both the upstairs and downstairs operating. Now, each of those modes must meet the 350 CFM per ton, as well as when you get into fan watt draw, the 0.58 watts. So a little more difficult to do when you have just that single speed compressor. If you have a multi-speed compressor on a multi-zone system, you will test it just like a standard non-zone systems. For all of these, the airflow measurements shall be performed with the fan set at the speed used for air conditioning, which is usually going to be the highest fan speed setting within the FAU.
It can be measured with one of the methods below: the plenum pressure matching method, the flow grid method, the power flow capture hood method, and traditional flow capture hood method. So these are the four methods used by using the four different pieces of equipment that we talked about in previous slides. So the plenum pressure matching method. When supply plenum pressure measurements are used for plenum pressure matching measurements, a 5/16 of an inch or 8 millimeter diameter hole for a static pressure probe, or HSPP, or a permanently affixed static pressure probe, PSPP, shall be provided as shown in figure RA 3.3-1. And this is an example of what those access holes would look like and the location of them. So the hole location shown in figure RA 3.3-1, which is on the right hand side, can be applied to any one of the four sides of the coil box or supply plenum. The hole location shall be labeled Title 24 Supply Plenum Measurement Axis in at least 12-point type. Now keep in mind that if for some reason the construction of the house and the location of the unit does not allow for an installer to drill those holes or to have access to those holes due to framing or structural issues, it is okay not to have the holes drilled for the Herzwater, I mean you, basically to see that they're not drilled, but it has to be verified by you to make sure that there is an actual reason of why those holes were not drilled. If the plenum is accessible and the holes are not drilled, that is going to be a failure on our part. So even if the system passes the adequate airflow and fan wall draw, but yet the holes are not drilled in the system will be a fail. So keep in mind that exception when it comes to those access holes in the plenum. And then, as I said, the system that cannot conform to the specifications for the hole location shown in figure RA 3.3-1 shall not be required to have holes. However, if the supply plan and pressure measurement are required for compliance, an alternate location that provides access for making an accurate supply plan and pressure measurement shall be used. The fan flow meter shall be attached at an inlet to a return duct from the condition space with grill and filter removed. If multiple returns are present, block off the ones not being used for this test. Ideally, you'd want to use the main return for this particular test. If the system is not, again, it's not a multi-zone automatic dampen system, the fan flow meter may be attached at the air handler blower compartment door as an alternative. And again, it may be attached. It doesn't have to be attached in such a way. The fan flow meter shall be attached at a point where the airflow through the system will flow through it. When the air handler blower compartment door attachment alternative is used, an air barrier must block the air handler inlet from the return duct system. And that's a example of what we're talking about. So if you are attaching the fan flow meter to the actual blower compartment door, you have to block off the return plenum completely so that air doesn't blow back into the return system. All registers shall be in their normal operating conditions. And then the static pressure probe shall be fixed to the supply plenum at the location previously specified so that it is not moved during the test. So the pressure probe will go into the hole that was drilled in the supply plenum. If the fan flow meter is to be connected to the air handler outside the condition space, then the door or access panel between the condition space and the air handler location shall be opened. Place the pressure probe in the supply pressure measurement hole described previously. Adjust the probe to achieve the highest pressure and then firmly attach the probe to ensure that it does not move during the system airflow test. If the probe happens to move or vibrate or shift during the test, it will skew your readings. With the system fan on at the maximum speed, which is the cooling speed, you want to measure the pressure difference in pascals between the supply plenum and the condition space. The recorded pressure is the target pressure to be maintained during the system airflow test. This is the PSP variable that you'll see in the equation coming up in a couple of slides. Attach the flow meter to one of the previously described locations. You want to turn on the fan flow meter, and you want to adjust the fan flow meter until the pressure between the supply plenum and the condition space matches the pressure measured in step 3. So you're going to be equalizing the pressure between the fan flow meter and the actual system. Then you'll record a flow through the fan flow meter. This is the diagnostic system airflow, or QAH, in the equation that you'll see in the next slide. In some systems, system fans and fan flow meter combinations may not be able to produce enough flow to reach the matching pressures due to problems that you might encounter. In this case, record the maximum system flow, which is referred to as the Qmax in the equation we're about to see, and pressure, or Pmax, between the supply plenum and the condition space. And this is the formula that I've been mentioning in the last couple of slides and the variables that we covered so far. So the following equation shall be used to correct measure system flow and pressure, which we've referred to as Qmax and Pmax, to operating conditions at operating pressure, which is the PSP. So the formula is the air handler flow, which is what you're trying to find, referred to as QAH, is equal to Qmax times PSP divided by Pmax to the 0.5 power. So let's look at the variables that are part of this equation. So the PSP, we talked about it. It's the pressure difference in pascals between the supply plenum and the condition space. This is the value that you found in step 3. The QAH is the air handler flow, which is basically what you're trying to find. You have the Qmax, which is the maximum system flow, and the Pmax, which is the maximum system pressure. So let's plug those numbers into the equation and see how it works. So the variables that we have for this example is the PSP, which we have at 20 pascals. You have the Pmax, which is the highest system pressure we're able to measure, which is 19 pascals. And you have the Qmax, which is the maximum system airflow that you can measure, which is 1600 CFMs. So the formula again is air handler flow, which is the QAH. That's what you're trying to find. It's the Qmax, the maximum system flow, which in this case is 1600, times the PSP, which is 20 pascals, divided by the Pmax, which is 19 pascals, raised to the 0.5 power. And this is what those numbers look like. So you have 1600 times 20 divided by 19 raised to the 0.5 power. 20 divided by 19 is 1.05 raised to the fifth power. 1600 times 1.03, and that gives us a final adjusted air handling flow of 1648 CFMs. Airflow is always measured in CFMs. Remember that. We mentioned that earlier. Now we're going to move on to verifying the system airflow by using the flow grids. The supply pressure measurement holes are required as previously described. The flow grid shall be attached at a point where all the system air flows through the flow grid. In order to do so, you would have to remove the filter and then reinsert the flow grid in replacement of it. All registers shall be in their normal operating conditions. If there are multiple return grills in the duct systems, flow grids may be used to measure airflow at the return grills, but only by installing a flow grid in each return grill and making simultaneous measurements of all return grill airflows. Place the pressure probe in the supply pressure measurement holes previously described. This is the same as we did before during the plenum pressure matching method. You want to adjust the probe to achieve the highest pressure and then firmly attach the probe to ensure that it does not move during the system airflow test. With the system fan on at the maximum speed, which is the cooling speed like we talked about before, you want to measure the pressure difference in pascals between the supply plenum and the condition space. This is the PSP variable you'll see in the equation coming up in a couple of slides, and it's the same as we talked about in the previous equation during the plenum pressure matching method that we covered. The recorded pressure is the target pressure to be maintained during the system airflow tests. You then want to remeasure the system operating pressure with the flow grid in place. You then measure the airflow through the flow grid and the test pressure. If multiple flow grids are present, you want to sum the flows through each of the flow grids. You then apply those variables you collected to the following equation. So the following equation for the air handler flow shall be used to correct flow through the flow grid, which is the Q grid, and the pressure, which is the P test, to operating conditions at operating pressure, which is PSP. So the formula is air handler flow, which is QAH, just like before, equals the Q grid times PSP divided by P test raised to the 0.5 power. And again, PSP is the pressure difference in pascals between the supply plenum and the condition space. QAH is the air handler flow, which you're trying to find. The Q grid is the airflow through the flow grid. If you have multiple grids, you want to add those up together. And then you have the P test, which is the test pressure with flow grids in place. And again, we're going to be using the same variables that we used before, just for a different particular equation. So once we plug those in, we have 1600 times 20 divided by 19 raised to the 0.5. And again, with the same variables, you're going to be coming up to the same results. So the air handler flow again is going to be 1648. Now for the power flow capture hood method, all registers shall be fully opened, the air filter shall be installed, and the flow capture area has to be at least as large as the return grill in all dimensions. So as you can see for the picture at the bottom, the flow hood capture hood has to completely cover the return grill. That means that the edges of the capture hood have to fully touch the drywall. They cannot be on the edge of the grill, they cannot be touching the metal. They have to fully enclose the register grill. You want to turn on the system fan at cooling speed and measure the airflow of the return grill to determine the total system return airflow. If you have multiple return systems, the total system return airflow, which is the QAH and CFM, shall be the sum of the airflow measurements at each of the system's return grills. That means that if you have more than one return grill, you want to measure them individually and then add them together. For the flow hood, for the traditional flow hood capture method, it works the exact same way. All registers shall be fully open, the air filter shall be installed, and the flow capture area, again, has to be at least as large as the return grill in all dimensions. If for some reason your capture hood cannot cover the whole grill, again, like we talked about earlier, you either have to build an extension in order to allow the flow hood to cover the whole register, or you can buy a pre-made extension from one of the manufacturers. And again, you want to turn on the system fan at the cooling speed and measure the airflow at the return grills to determine the total system return airflow. For multiple return systems, the total system return airflow, QAH and CFM, shall be the sum of the airflow measurements at each of the system return grills. Again, if you have more than one return, you measure them individually and you add them up together. And that will be your total system return airflow. So there are different reasons that you might see low measure system airflow, and these are a couple of things that you diagnose quickly in the field. So the fan setting might not be set on high when testing. Again, you gotta have to test the system in the highest setting possible, and generally speaking, it is the cooling system. Now, something to think about: if you're conducting this test during the winter and the temperature outside is less than 60 degrees, if you're going to turn on the air conditioning system, it might be a good idea to disconnect the actual condenser. If the condenser actually comes on and it's below 60 degrees, you run the chance of freezing the lines, and in that case, it's going to permanently damage the compressor. So if you're below 60 degrees and testing for this particular test, meaning that you'll be turning on the cooling system, which is the highest speed setting for the system, pull the disconnect on the condenser first so that the blower will run at the highest speed, but the condenser will not kick on. And then obviously remember to turn it back on when you're done with the test. Another reason for this particular test to fail, or reason for low measure system airflow, is return duct leakage. In the picture on the right hand side, obviously that's an extreme scenario. It looks like you have a whole return duct just disconnected. But nonetheless, leaks in general will affect your system airflow, and especially return duct leakage. Another reason could be damage or blockage to return ducts. So as you can see, you have crimped ducts. Obviously, if you have a duct that's crimped, collapsed, disconnected, whatever it may be, you're gonna see low measure system airflow. So it's another item of interest. And also oversized, undersized return ducts and or return grills. So this is really just a design item. If there was a problem with the way the system was designed in regards to undersized or oversized return ducts or grills, there's not much that you can do. Nonetheless, if the system fails, the system fails. But if you check for everything else that we talked about and you cannot find anything, it might be a design issue. So at that point, they would have to go back to the design stage and figuring out whether the system was actually installed properly into standard and or was designed properly to begin with. And now we're going to move on to fan watt draw. So the fan watt draw can be measured with one of the following methods. You have the portable watt meter, or then you can use the analog utility revenue meter or the digital utility revenue meter. When taking the reading for the portable watt meter, first you want to have the registers being fully open, and the air filter shall be installed. You want to turn on the system fan at the maximum speed, which is usually the cooling speed as previously described. Include the outdoor air introduction if the ventilation is provided through return duct system. So if you have a CFI system, ventilation system, like we talked about previously, where you have a fresh air vent coming into the HVAC system, you want to have that working and coming in properly in operating conditions. You will then take the measurement of the fan watt draw, or W fan, directly from the metering device. In the picture that you see on the right hand side, that's a plug-in meter. You'll be able to use this meter for an HVAC unit that actually has a plug-in outlet and not hardwired into the electrical system of the house. So basically, you'll take the reading off the meter. If it is at hardwire systems, you would just have the other type of watt meter that basically hangs on the actual wiring of the furnace. So you will take that reading, and that is your watt draw from the actual furnace. We'll talk about what to do with that measurement in a sec after we're done talking about the other two methods. If you're going to be measuring the watt draw from the analog utility revenue meter, this is the setup. So all the registers again shall be fully open. The air filter shall be installed. You then want to go to the breaker panel and turn off every circuit breaker except for the one exclusively serving the air handler. So everything should be turned off except for the main, obviously, and the one connected to the air handler. Again, you'll turn on the system fan at the maximum speed, which is the cooling speed, like we talked about plenty of times before. And again, include the outdoor air introduction if the ventilation is provided through the return duct system. You will then want to go to the utility meter outside, the analog utility meter. If you look at the utility meter, you'll see a number with a KH somewhere on the particular meter. In the picture that you see here, the KH is found on the bottom right hand side. For the most part, that's where you'll find it the majority of the times. But nonetheless, if it's not located there, just look for a number that has the KH designation next to it, and that'll be your KH factor. You will then want to count the number of full revolutions on the meter wheel over a period exceeding 90 seconds. So when we talked about earlier, you needed to have a stopwatch, and that's what the stopwatch is for. So you're always going to count full revolutions, but no matter what, you have to count for at least 90 seconds, the number of revolutions. You want to record the number of revolutions and time period used during the count in seconds. So it has to be at least 90 seconds. It can be more than 90 seconds. You want to record the number of revolutions, always in full numbers, not decimals, not percentages or fractions of it. And then you want to record the number of seconds that you use to measure those revolutions. You will then plug in those numbers into this particular formula. So you're going to compute the air handler watt draw using the following formula. The W fan, which is the watt draw. The formula is going to be the KH factor that you got from the actual utility meter. So in our case, it was a 7.2, according to the picture that we saw a couple of slides ago, times the NREV, which is the number of revolutions that you counted, times 3600. 3600 is going to be a constant. That 3600 is never going to change. Divided by the time in seconds that you use to count the revolutions, which is the TREV. And again, this is what the variables stand for. So W fan, again, this is the air handler fan watt draw, which you're trying to measure. The KH is the KH factor that you grabbed from the utility meter. The NREV is the number of meter revolutions. And remember, whole numbers only. You're always going to round up if need be. And then TREV, which is the time used to count revolutions, and again, always in seconds. And this is the example that we're going to use on the variables associated with it. So the KH factor is 7.2 from the utility meter. We counted 3 revolutions in 90 seconds. You will then plug in our numbers. So we have 7, which is 7.2 rounded down, times 3, the number of revolutions, times 3600, which is a constant number always plugged into the formula, divided by 90. So that gives us 75,600 divided by 90 seconds, which gives us a watt draw of 840 watts for that particular scenario. And that's the number that you would use moving forward. After you're done recording the watt draw that you just calculated, please remember to return all circuit breakers to their original positions. You don't want a homeowner calling you telling you nothing in my house is working because you forgot to turn them back on. So just go back to the breaker panel and turn everything else back on. For the digital utility revenue meter, it's very similar. So all registers shall be fully open. The air filter shall be installed. And again, you're going to turn off every circuit breaker except the one exclusively serving the air handler, just like you did for the analog utility revenue meter. And again, you will turn on the system fan at the maximum speed, usually the cooling speed. And again, include the outdoor air introduction and ventilation is provided through the return duct system, just like we did before in the previous methods. Here you see a picture of a digital revenue meter. So all you're going to do in this particular scenario is read the watt draw from the digital utility meter digital display. It's going to give you the number directly. You then will return all circuit breakers to their original positions. Now that we have both our numbers, we can actually figure out whether the system passes or fails. So there's two steps to determining that. First of all, we want to figure out whether the amount of airflow being pulled from the system, from the return system, actually meets the specifications based on the tonnage, on the AC tonnage of the system. So in our previous examples, our measured system airflow rate was 1600 CFMs. We know that the tonnage is 4 tons. Keep in mind that for the adequate airflow, it always has to be 400 CFMs per ton. So all we're going to do is we're going to divide the 1600 that we measured, and we're going to divide it by the number of tons. And that gives us 400 CFMs per ton. So in this particular case, we know that the system does meet the forced system airflow requirement. In order to determine the forced air system fan efficacy, we're going to have to compare the actual system airflow of CFMs with the watt draw that we measured earlier as well. So this requires simultaneous measurement of the system airflow rate and watt draw as previously described. In this particular example, the watt draw is 600 watts and the airflow rate is 1800 CFMs. All we're going to be doing is we're going to be dividing the watt draw divided by the airflow rate, which is 600 watts divided by 1800 CFMs. That gives us a fan efficacy of 0.33 watts per CFM. So the measured value for the fan watt draw shall be divided by the measured value for airflow rate to determine the fan efficacy. So the fan efficacy for this particular scenario is 0.33. If you look at the CF1R and the CF1R tells you that the fan watt draw is required, it will give you the target of what the fan watt draw fan efficacy will be. The number that you measured cannot be more than the target numbers on the CF1R. So by default, the fan watt draw for a system is 0.58 per CFM of fan efficacy. So in this particular case, is 0.33. In this particular scenario, if 0.58 was the target, 0.33 is the actual measure of fan watt draw, that would be a pass. Now keep in mind that 0.58 is the default and is the prescriptive standard. Nonetheless, the number could be different. So always refer to your CF1R applicable to your project for this target number.
In order to comply with either the system airflow requirement or the fan efficacy requirement, the following criteria shall be met. Number 1, the system airflow, or CFM per ton, shall meet or exceed the system airflow compliance criteria that's specified in either the standards as a prescriptive requirement or on the certificate of compliance as applicable. So the certificate of compliance is the CF1R. Now, if they're using the prescriptive method, your standard design minimum target is going to be 350 CFM per ton. But if you are using the performance method, that minimum target can be changed. So you always want to go to your CF1R to find that minimum target value. Again, prescriptive value is 350 per ton for a new system.
The calculated value for fan efficacy, which is the watt per CFM measurement that you took, that you calculated, shall be equal to or less than the fan efficacy compliance criteria specified in the standards, again, or in the certificate of compliance, which is the CF1R, as applicable. And as I stated before, the standard design maximum target is 0.58 watts per CFM. And again, always refer to the CF1R to find the specific requirement for your project. Also keep in mind that depending on the type of system you're working on, you're going to be testing it in different ways. So for single zone air distribution systems with multi-speed compressor systems or variable speed compressor systems, but regardless single zone, you want to shell verify the airflow and the fan efficacy for system operation in cooling mode at the maximum compressor speed and the maximum air handler fan speed. There's going to be different ways you test single zone versus multiple zone systems. So we're going to be covering multiple zones next. If you have a zoned air distribution system, as I had stated, you shall meet both the airflow and fan efficacy criteria in every zonal control mode. Multi-speed compressor system or variable speed compressor systems shall only be required to verify airflow and fan efficacy for system operation in cooling mode at the maximum compressor capacity and maximum system fan speed, with all zones calling for conditioning. Keep in mind that in that particular scenario for the second bullet, that only applies to multi-speed compressor systems or variable speed compressor system as well. So how do you determine whether a system is single zone or dual zone or multiple zone? And these are some of the items that you can look for to realize whether it's a multi-zone system or a single zone system. So first of all, you're going to see motorized or actuated zone dampers on the supply ducts. You're going to see multiple thermostats or temperature sensors in an area served by a single system. So you're going to have one HVAC system but multiple thermostats. You're going to see a control board on or near the air handler with low voltage wires going to the thermostat's temperature sensors and to each damper. So you're basically going to see the control board that goes to the individual dampers, and or you're going to see a bypass duct and a damper to the bypass ducts. Those are all good indications that you're working on a multi-zone system. And this is an example of motorized or actuated zone dampers on the supply ducts. Multiple thermostats or temperature sensors in the area served by a single system. A control board on or near the air handler with low voltage wires going to the thermostat and temperature sensors and to each dampers. You're going to see a boulder like this, as you can see, mounted near or on top of the furnace, and multiple wires going through different dampers. And then a bypass duct and or damper. You can see here you have a bypass duct that's going from the return plenum to the supply plenum. Obviously a really good indication that that is a zone system. This is a diagram that shows how a zone system actually works. So you have a single air handler with a supply plenum, and then you have the supply ducts, the main supply ducts that go to 2 different zones. On the left side you have zone 1, and on the right side you see zone 2. In this particular example, only one zone is calling, meaning that only one thermostat is turned on, and it's actually calling for air to be supplied to that area of the house. So the zone 2 damper stays closed, and the air handler would only serve the area that's connected to the first thermostat or zone 1. So when we talked about the only way to test single speed compressors is to have all zones calling, you basically want to have all the thermostats on to cooling. Therefore, all the dampers will be open and the system will be servicing the whole house at once. When a zonally controlled forced air system is installed, the following shall be verified to determine compliance. And we're talking about visually verified. You have to visually verify that these items, either one of these items is present. So 1, a visual inspection shall confirm that bypass ducts that deliver conditioned supply air directly to the space conditioning system return duct airflow are not used, or if the certificate of compliance indicates an allowance for use of a bypass duct, the bypass duct shall conform to the specifications given on the certificate of compliance, and that is the CF1R. So basically, the CF1R will tell you if bypass ducts should be used in the system or not. If they're not supposed to be used but they're present, it will be a fail. If they are supposed to be used but they're not present, it will also be a fail. So you have to visually verify whether they are there or not and install to standard depending on what the CF1R states. For multi-speed and variable speed compressors, if this type of compressor is modeled, it must be installed and verified. Again, the CF1R will tell you. There are several features that indicate that a condenser is multi-speed. Product tags, labels, and marketing names that indicates 2-stage, dual-stage, multi-stage, etc. 2 compressor observed by looking down through the condenser fan, or high and low capacities or nominal tonnages indicated on the nameplate. The only definitive way to determine if the condenser is multi-speed or variable speed is to record the make and model number and find the manufacturer specifications. And now we're going to be mentioning the forms used and associated with the test we just talked about.
The CF3R MEC22H is the verification form for fan efficacy or fan watt draw. And the MEC 22A version is for the all zones calling only method. It's 2 pages long. The MEC 22B variant is for every zonal control mode and is 3 pages long. The CF3R MEC 23H is for space conditioning system airflow rate, and the MEC 23 variant A is for the all zones calling only method. It is 3 pages long. The MEC 23 variant B is for the every zonal control mode method and is also 3 pages. The MEC 23C variant is an alterations form, and this is what we call the best that I can do. It is 3 pages, and it is for alteration systems that do not meet the minimum prescriptive airflow value. And finally, the MEC 23D is for systems that are not cooling, but you still need to measure that airflow when you have a CFI system installed. It's the all zones calling only, measurement only system, and is 3 pages.
If you have any questions about anything that we talked about in this PowerPoint, feel free to call us, leave us a message through the messenger system, or write us an email.